Welcome to the 9th video in the series called Video Standards, Signals, Formats, and Interfaces. The current state of global standardization in the audio realm is far from perfect. The global adoption of the integrated loudness standards and the concept of audio levels normalization were two big steps forward. Today you will learn more about audio and why it's so important for video. The word video in Latin means I see. The word audio means I hear. Picture has its beauty, but only sound can spell out a story. In other words, video imagery requires accompanying sound. Among many parameters used to describe subjective perception of sound airwaves, the most important for video applications are comfortable loudness range. For example, normal conversation level is from 40 dB to 60 dB. Audible frequency range, from 20 Hz to 20 kHz. Maximum sensitivity frequency range, approximately 350 Hz to 5 kHz. Analog audio professional interfaces use mostly XLR connectors and shielded twisted pair cables. The main digital audio format is the AES-3 format, used worldwide and jointly developed by the Audio Engineering Society and the European Broadcasting Union. An AES-3 signal can carry two PCM uncompressed channels, meaning one stereo pair of audio data up to 24 bits at 192 kHz. A consumer-grade variant of AES-3 is known as SPDIF. Digital AES-3 signals can be transmitted by various physical interfaces. AES-3 is the preferred interface format for professional applications, and there is a noticeable trend towards the AES-3-ID format on BNC connectors. Analog audio levels are usually mapped to a dBu scale, which represents the root mean square audio voltage referenced to the nominal analog RMS voltage of 0.775 volts. An important and unpleasant fact: there is no audio equivalent of fixed reference white video level, meaning there is no nominal audio signal reference level. Instead, audio engineers use test or alignment level, which serves only for the hardware gain calibration, and audio program peak meters, ppm, or volume unit, VU meters, to check them. The diagrams illustrate the complete chaos, or you may call it creative freedom, that rules in the analog realm. dBFS means decibels relative to full scale, that is, to the maximum peak level of the digital signal. For 24-bit digital audio, the maximum magnitude value is 2 to the 23rd power minus 1. Unfortunately, there are two schemes for mapping the analog audio dBu levels to the digital audio dBFS levels: EBU R68 and SMPTE RP155. And they're mapping 0 dBu level to different points on a dBFS scale. The difference is 6 dB. Note that not all analog levels are available in the digital domain. The upper 2 dB or even 8 dB are clipped off. Loudness control and monitoring is needed in production, post-production, and distribution of audio-video content. The widely used peak program meter, known as ppm, allows us to check three important levels: measurement level, alignment level, and permitted maximum level. Traditional ppm meters have been combined with, but not replaced by, the measurement of momentary loudness, short-term loudness, and very importantly, integrated loudness, plus true peak value. First set by the famous EBU R128 standard, this methodology was refined in ITU-R VS9 standard, then became mandatory in many countries. An integrated loudness meter gives only one number per clip or program segment. Much more useful information about audio tracks can be found in the loudness timeline profile. VideoQ has developed software tools for the automated measurement of integrated loudness values and momentary loudness timeline profile arrays. The results are available in two formats: machine-readable JSON reports and plot images for human QA/QC operators. Modern multi-format, multilingual audio production requires simultaneous processing of multiple audio channels. AES-10, also known as Multi-Channel Audio Digital Interface, or MADI, is an AES-3 compatible standard that carries up to 64 channels of digital audio. But for video applications, the most important step forward was the possibility of embedding audio data within SDI connections. The big advantage of embedded audio is the automatic compensation for video delay. The audio data latency is always the same as the video latency. Up to 16 AES-3 channels, stereo pairs, can be transmitted via SDI interface together with the video data. Well-known AV sync, otherwise known as lip sync problems, are often caused by the video and audio data processing, and usually by compression codecs. Different organizations have published quite different tolerance values for this error, ranging from very small, like plus or minus 22 milliseconds, to relatively large, up to 45 milliseconds audio ahead of video, or 125 milliseconds of audio after video. The main remaining issue is how to measure this parameter. So VideoQ made a set of hardware and software tools for measurements and audiovisual assessment of AV latency and AV sync errors. This video was prepared for you by a team of experts. Produced and narrated by Joseph Mark, a member of SMPTE's HDR committee. Written by Dr. Victor Steinberg, co-founder and president of VideoQ, technical awards winner and author of the Video Standards book. Conceived by Roderick Snell, co-founder of Snell & Wilcox and winner of several technical Emmys and Queen's Awards. Technical consulting by Maxim Levkov, author of the Video Encoding Cookbook. This video series is brought to you by VideoQ, and you can download these slides and this video from VideoQ.com. VideoQ makes products and services for all sorts of video and audio processing and quality assurance. Based in Silicon Valley with software developers and distributors in several countries. Thank you for watching.